Good morning, everyone. I hope that we have had a safe and warm past couple of snow days. Hopefully you're able to get out and do something fun, or at least stay cozy inside. We're going to pivot a little bit here today. So we're going to look at the first section in our next unit. We will still be taking our Chapter 7 test quiz whenever we come back, which is hopefully tomorrow. But just so we don't get further behind in our pacing, we're going to go ahead and look at this first little section, which this next unit is over sequences and series. And for a lot of us, it's been a while since we've seen sequences and series. So this first section, we're going to do a little bit of calculus stuff with it, but it's also just kind of a review to ease our way into working with series. Alright, so to begin with, it's helpful that we know what it is that we're dealing with. So remember that a sequence is just a list of numbers and that are in a particular order. We call those numbers terms, and those numbers are usually based on some sort of rule or formula. So, the terms in a sequence could be something as simple as, 2, 4, 6, ... So our rule is that I'm adding 2 each time. Now, our notation, like I said, we call each one of those things a term. So our notation is going to be, we use it as A sub n represents the whole sequence. N is called our index, and our index represents the number of term that you're on. So A sub 1 would be the first term, A sub 2 would be the second term, A sub 3 would be the third term, and so forth. The index must be an integer. So we're not going to look at the 2.5 term, right? We're just going to look at the first, the second, the third, and so forth. And so that's pretty basic definition, but there's a lot that we can do with sequences and series just based upon these very simple lists that we can start with. So again, kind of a blast from the past. Hopefully we recall our two types of, so these are our two special sequences that you've seen in the past. We're going to get a whole lot more. We're going to be dealing a lot more with series than we are with sequences, but sequences lead into series. And so we're going to learn all about the different types of special series that are out there. But the two that we've seen in the past are the arithmetic, where remember that your arithmetic sequence is where you add something each time to get the next term. So the example that I showed you of our our even numbers, that would be an arithmetic because I was adding 2 each time. Versus our geometric is where I multiply by something each time. Now, these do have special formulas. There's a lot of special formulas that go into them. But in particular, today we're just going to be looking at the general. So our general formula, so again, remember A sub n just represents kind of that sequence. So for an arithmetic sequence, A sub n equals A sub 1 plus So a sub 1 being our first term, n minus 1 times d, where again, d is that, we call it the common difference, or what we're adding each time. For a geometric sequence, it is a sub n equals a sub 1 times r to the n minus 1 power, where again, r is what we are multiplying by each time. Of these two, we're going to need to know our geometric more so. We're going to look at an arithmetic today, but our geometric is what's going to come up as we continue on. So let's write out the terms for the following sequence. So remember again that our sequence is just our rule or our formula. So to find each of our terms, we're just going to plug in. So like on our first one, we would plug in 1 to find our a sub 1. And notice here that we get 3 plus a negative 1, which gives us 2. Then if I look at my a sub 2, it's going to be a very similar process. And now I'm squaring it. So now I have 3 plus a positive 1, so I get 4. Notice that if I continue this pattern, I'll plug in 3 next and 4 next. But because we're just either raising it to an odd or an even power, those numbers are just going to continue to go back and forth. And so this is what we call an alternating series. There are different types of alternating series. This one is alternating because it's alternating between two numbers. We'll also see more often our alternating series are going to be because they're alternating between positive and negative. So on this next one, again, I'm going to plug in my a sub 1. So if we plug in a sub 1 this time, notice that we have a 1 on top divided by, we would have 1 minus 2. So we would just get a negative 1. When we plug in our 2, we would get 2 divided by 1 minus 4, which is going to give us a negative 3. Let's go up to 3 terms. If I plug in 3, we get 3 divided by 1 minus 6, which would give us negative 5. So in general, our terms, we said the first one was negative 1, then we would get negative 2/3, negative 3/5, and so forth. This last one, we're now dealing with both a squared and a 2 to the n power. So again, plugging in my a sub 1, I have 1 squared, which is 1, 2 to the first just gives me 2. So our first term is just going to be 1. My a sub 2, now we have 2 squared, which gives us a 4 up top, and then 2 to the second is also 4. Minus 1 gives us a 4/3. Plugging in a 3, I get a 9 up top. 2 to the third now gives us 8 minus 1, which gives us 7. So again, Nothing super complicated. This is more just helping us to get used to that notation. Also just helping us get used to looking at what some of the different numbers can be. Because we are then going to have to be able to take this and work our way backwards. So now we're going to start with a sequence and have to figure out what the rule is based upon what they give me. So notice on this first one, I have -2, I have 5, I have 12, I have 19. So the first thing that's going to be helpful is to kind of break apart what we have or what's going on. So notice that as we look at these, I'm starting at -2, so that's usually a helpful place to start. Is that not to start at -2, but that we start with identifying what our first term is. Then notice that this will be an arithmetic sequence because we are adding 7 each time. And that's helpful because we don't have to then find kind of the rule by ourselves. We can use that rule that I gave earlier. So remember that that was the a sub n equals a sub 1 plus n minus 1 times b. So our a sub 1 we said was -2. Remember that our n is acting as our variable, so it's going to stay in there. And then 7 is what we are multiplying by each time. So if I were to go ahead and simplify this, just because we don't tend to leave the parentheses in there, I would get a 7n, and then I would have a -7 minus 2 gives us a -9. So that would be our final answer. So now looking at the second one, I have 3, 6, 12, 24. Again, let's start by finding where our first term is. So in this case, our a sub 1 is 3. Now we might say like, okay, on the first one, I'm adding 3, okay? But then notice that that kind of falls apart for my third term. So if I added 3 to 6, I would get 9. So that's not the case. But do notice that this time if I take 3 and I multiply by 2, I get 6. If I multiply by 2, I get 12. If I multiply by 2, I get 24, and so forth. So this time we are multiplying by 2, which means that this is a geometric. So again, I can just use that formula that we had previously. And then I can just plug in. So my first term is 3. My r, which is what we're multiplying by each time, is 2. And then I'm just leaving in my n minus 1. Our geometric are a little bit easier because there's not any simplifying that we have to do. Other than I would be careful that you don't multiply those two together and try and put 6. That's a common mistake because notice that I do have an exponent and they don't have the same exponent, and so I cannot combine the bases. So that would just have to be our answer. Now, these last two are going to be a little bit different because they're not going to be some of our special formulas. We're going to have to pick them apart a little bit more. And also what's a little bit different is that we have fractions, which is fine. Usually the easiest way to look at these is to break it apart into like the top and the bottom. So especially on this first one, notice that the top isn't changing. And so that's really helpful because then we can just go ahead and label our top is 1. Now on the bottom, notice that I have 2, 4, 8, 16, and so forth. On the first one, I don't technically have a denominator, so sometimes it can be helpful to go ahead and write that this is technically going to be over 1. So I have 1, 2, 4, 8, 16. So those numbers, again, should look kind of similar to what we dealt with on part B, I'm starting at a different number, but notice again that we are multiplying by 2 each time. So if we think about it, using that same formula that I had before, it's still geometric, but it's only geometric on the bottom. So I'm still going to have my a sub 1 is first. Well, but a sub 1 is 1, so I don't really have to write that. I'm multiplying by 2 each time, so that's our r value. And then I have to the n minus 1, which makes sense because if my first term is 1, I plug in a 1, 1 minus 1 is 0, 2 to the 0 is 1. Then if I plug in a 2, 2 minus 1 is 1, I get a 2, which is why we get 1/2, and so forth. Now, on our next one, it's a little bit more complicated. It's not even partially a geometric, which is fine. Also notice that both our top and bottom are changing, which means that we're going to need to have n's in both the top and the bottom. So I'm starting with a 1, a 4, a 9, a 16, 25. Hopefully we notice that all of those are going to be our perfect squares. And so then we just kind of decide where we're starting. So on my first term, I have a 1. Well, 1 squared is 1. On my second term, I have a 4. Well, 2 squared is 4. So notice that whatever we get, so whatever term we're on, which again is n, I am just squaring that. So that's going to be my top. Now on the bottom, we got to do a little bit more work. But notice then that they almost kind of make diagonals with one another. So I have a 4 on the bottom, and that's the numerator of my next term. 9 on the bottom, that's the numerator of my next term, and so forth. So it still looks like we're squaring stuff because we're getting those perfect squares, but notice that it's like the next term that we're squaring. So in order to get the next term, we would say n plus 1 squared. And so again, that's just an example of how sometimes we're going to have just like kind of unique formulas. It's not necessarily going to follow one of our other patterns. All right, so moving into maybe a little bit more calculus-y of our sequences. So we can take the limit of a sequence. And so when we take the limit of a sequence, we're specifically looking at what is happening as n, or the number of terms, goes to infinity. So we're looking at the limit as n approaches infinity of a sub n. And again, our n's still have to be integers, and they also have to be increasing. So we're going to be going up the first term, the second term, the third term, and so forth. And we have two different options here. Our terms can be going towards a particular number. If my terms seem to be approaching a particular number, when we take our limit, just like when we've taken limits in the past of something, and they approach a particular number, we're going to say that that converges. So this is similar to what we did with our improper integrals. So if my limit exists, we can say that the sequence converges. Now, if my limit does not exist, we're going to say that that sequence diverges. And in that case, I would either get a positive or negative infinity. So sometimes it'll be similar to the language that we saw with our improper integrals, where it'll say like, show that this sequence converges. Or it'll say like, if possible, find the number that the sequence converges to, because sometimes the answer is that it diverges. And we'll look at an example of one of those. Some other things to think about, just similar to like our limit properties that we had, we also can use those same properties when we're taking the limits of our sequences. So we can multiply by scalars, meaning that if I have some sequence and I know that that sequence approaches L, then I can just take that constant and multiply it together. if I'm taking the limit of two separate, or I can break those two sequences apart, then we can also just add together those limits. Same goes for multiplication and division. The only thing about division is, again, just like normal, this thing on the bottom can't approach 0. And so as we do some of these, it's helpful sometimes to either break them apart or look at them separately, just like we've done with, our other limits and derivatives and things like that. So again, here we are, it says that show that this sequence converges. So we want to take our limit, because we said that in order for it to converge, my limit has to exist. So I have a limit as n goes to infinity of my a sub n, which is n squared divided by 2n minus 1. So again, as always, remember, I can't technically direct substitute infinity, but we can think about what the behavior of the top and the bottom would be doing. So notice that if I plugged in, quote unquote, n squared, infinity squared is still just a big infinity. On bottom, I have 2 to an infinity, which is an even bigger number. If I subtract 1, not doing all that much. So we get an infinity over an infinity, which is one of our one of our indeterminate forms. And it's one of our indeterminate forms that's already a fraction. So we can go ahead and use L'Hopital's rule. So taking the derivative of the top, I get 2n. Now, we do have to remind ourselves a little bit about our derivative rule here. So remember that the derivative of e to the x is just e to the x. Same thing with my other bases. I still just get a 2 to the n, or 2 to the x. But remember that we must also multiply by the natural log of whatever our base is. Okay, so again, thinking about what would I get if I could, quote unquote, plug in infinity. Well, notice 2 times infinity, still just infinity. I still have a 2 to the infinity on bottom, which is also still infinity. So we're actually going to apply L'Hopital's again. This time, if I take the derivative of the top, notice that I'm just going to get 2, and that's helpful. If I take the derivative of my 2 to the n again, still going to get 2 to the n. Notice that I would have to multiply by another natural log of 2, and so I'm going to have a natural log of 2 squared. Now I just have a constant on top, which is nice because I'm still getting that 2 to infinity on bottom. And so I'm still having a really large number on bottom, but I have a constant now on top. So a constant divided by infinity, remember, is just going to approach 0. So I got an L. My L is my limit. I got an actual number, not infinity or negative infinity. So we can say, therefore, a sub n converges. Yay! Alright, we're going to look at a couple of others. Again, we're deciding if these limits converge or diverge. Now, on some of these, it's not quite as easy as our other ones. Our last one was very algebraic. We could apply our previous algebra rules, and sometimes that'll be the case. We can apply algebra rules. There will be some cases where that's not the case. We have to do a little bit of thinking in order to be able to tell what's going on. So, and the reason for that is notice the bottom is very algebraic again, but our numerator is -1 to the n, and we've never really dealt with anything like that. So we kind of have to think through what that would mean. So again, my n represents integers, so I would plug in 1 first. So -1 to the first gives me a -1. Okay, well then, if I plug in a 2, -1 to the second gives me a +1. If I plug in a 3, -1, +1, -1, +1, and so forth. So notice that on top, this is what I was talking about earlier with that alternating series, that it's just going to alternate between -1 and 1. So it's not a constant in of the sense of like I have the same thing every time, but it is a constant in the sense that like it's just very, very small numbers, meaning 1 and -1 in the scheme of things. Because then also notice on bottom, this is just me thinking work, okay, because I can't actually plug in infinity, but infinity squared would still be infinity plus 1 is infinity, right? So I'm still getting this really big, large number on bottom. So since -1 and 1 are both pretty small numbers, I still have what we can consider a constant on top over infinity. So we can still say that this converges to 0. Now, on the flip side, if I'm looking at the limit as n goes to infinity of my cosine function, okay, so this time I'm plugging in, again, we're plugging in those integer numbers. So if I plug in 1, cosine of just pi is -1. Then I plug in 2. Cosine of 2 pi is a +1. Cosine of a 3 pi is going to be -1, and so forth. So again, we get those alternating values, but notice now that I'm not dividing by anything. Like that's the only value that we're getting. And so because it's alternating between those two numbers and nothing else is going on, we would say that this diverges because it's going to fluctuate or oscillate or alternate between -1 and 1. Now, this last one is very algebraic because again, I'm looking at the limit as n goes to infinity of 4n³ divided by n³ plus 1. There are two different ways we could do this. One, we could say, okay, that plus 1, not going to do a whole lot. Then my n³ are basically the same, so they're going to reduce out. I'm just going to be left with 4, and then my limit is just 4. Remember the very, like, algebraic-y way to do that is we divide the top and the bottom by the largest variable exponent on the bottom. So like these would go away, these would go away and be 1, and so this would be 4. I have a 1, and then again, because I'm looking at the limit as n goes to infinity, this is going to go towards 0. So I end up with a 4 divided by 1, which is why we just get 4. So sometimes we will have a more algebraic limit that we can deal with. Alright, so moving on, we talked about sequences now, but our other thing that we can talk about is series. And basically a series is the sum of the terms in a sequence. And hopefully you remember that, so this word sum is a good indicator that our notation that we're going to use here quite often, and we need to get used to it, is going to be a summation. So I have the summation of a sub n. So I am summing together all of the terms of a particular sequence. Now, a partial series means that we have finite terms. My number of terms ends. So I'm going from n equals 1 to some b value. So I would, add together a sub 1, a sub 2, a sub 3, all the way until I get to whatever term I'm going to. Versus an infinite series, it's kind of self-explanatory, but has infinite terms. And so now when we look at this, we're going from n equals 1 to infinity and beyond. And for the most part, we will look at partial series every once in a while, especially to aid us in doing other stuff. But where we're really gonna live is our infinite series. So again, that's just kind of some setup, remembering some vocabulary. So this time we're going to consider the infinite series from 1 to infinity. It is k this time. Sometimes we'll see k's, sometimes we'll see n's. They mean the same thing. We're okay with that. And we are going to list the first 4 terms, but we have to be careful because this is a sum now. Okay, so I'm still going to plug in 1 first, but I'm going to use an s instead of an a this time. So notice that if I plug in 1, I get 1 divided by 1 times 1 plus 1, which is going to give us 2. Now, this is the part where I said that we're going to be careful, because I am plugging in 2 next, but this is a partial sum, which means that I have to start by taking my first sum that I found, which was 1/2, and adding that to whatever I get when I plug in 2. So we have 2 plus 1 would give us 3. 3 times 2 gives us 6. So we have a 1/2 plus a 1/6. If I found a common denominator, I would have 3/6 plus 1/6, which is 4/6. Which we can also reduce to 2/3. My third sum is going to work very similarly. This time now, I would take my 1/2, add my 1/6. And then we need to add what we get when we plug in our third term. Now, I do realize that we already know what the 1/2 plus the 1/6 is. It's 2/3. But sometimes writing them out like this, with each sum individually first before we combine them, can be helpful, especially for this next part, where we're trying to find or look at patterns that arise. So notice that if I plug in 3, I get 1 divided by 3 plus 1 gives us 4 times 3 is going to give us 12. So if we add all of those together, we should get 9/12, or in other words, 3/4. Lastly, for my s sub 4, I have 1/2 plus 1 6 plus 1/12 plus, now when I'm plugging in 4 plus 1 gives us 5. 5 times 4 gives us 20. Adding those all together, we would get 48/60, which is 4/5. So looking at those now kind of as a list in and of themselves, we had that our S sub n equals, we got 1/2 first, then thirds, then 3/4, and then 4/5. So it says find an expression for S sub n, which this is kind of why I wrote them out as a list, because it's kind of the same thing that we were doing for our A sub n's for that second example where I needed to find the rule or the pattern. So notice here on top, my tops are changing, but it's just 1, 2, 3, 4. So it is just whatever our n is. Then on bottom, notice that they are also just going up by 1. But I'm starting, again, it's kind of like that one that we looked at, where my numbers are kind of diagonal from each other. It's 1 off. And so it is our n plus 1. And so my S sub n formula here, I can still have a formula. Even though it's not a sequence, a series can still have a formula. You just kind of have to break it down into what you are getting for each of those sums. Because notice that your formula for what we have for A sub n, which is what's inside of my summation, is not going to be the same as what your S sub n formula is. So we do have to do some work and figure out what each of the terms are for our sum in order to find that expression. And so then it asks us to make a conjecture about the series. And basically it's just kind of talking about, can we think about, okay, what's happening? Is it converging? Is it diverging? So let's think about if I'm looking at the limit as n goes to infinity of n divided by n plus 1. Again, we can think about that plus 1 doesn't really matter all that much. I just have n divided by n. Those reduce out, and I would just be left with 1. So this would be convergent. And it specifically converges to 1. Yippee! Now, let's look at what happens when I have something that is maybe not convergent. So, on this one, we could go ahead and write out the terms of here. It's not going to be as nice and pretty for this one because you do end up with a lot of fractions. I also wanted to give the chance to look at how we can deal with these in Desmos. So Desmos can do summations, just like our other stuff. Kind of like the same thing with integral. If you just start typing sum, so SUM, it'll give you a summation notation, and then it lets you plug in the bottom bound and whatever you want on top. I have then plugged in the formula it gave us here, okay? The bad thing is that it won't let you plug in an infinity here on top, so we do have to do just like a little bit of thinking, okay? So I put B, okay, as my slider, because when you type in another variable up here, it's going to like give you this prompt that says like add slider, and so then you click yes, and so then down here we can then, I'm starting at 2, so that means that if I plug in 1, notice that I'm going to get 1/3. That's, I think I can go backwards, right, 1/3. I plug in 2, that means now I'm adding both of them together. So then I'm going to continue on to look to see if I see a pattern, kind of like we did for our last one. But notice that like as my top bound gets bigger, so do my numbers. So like what's happening here is that my sums are just getting bigger and bigger and bigger and bigger. So if we were to look at the limit of this, my limit would just be infinity, which means that this sum diverges. Just like with our A sub n's, if it doesn't go to a particular number, then it is divergent. If we wanted to, just to kind of see what it looks like instead, so that last one that we did was a 1 instead on top. and it was k times k plus 1. So notice now, when we start all the way back here, right, we should get the same stuff that we got for arts, right? At 1, I get 0.5. At 2, we get 0.67, and so forth. But now notice that as my values get larger and larger and larger and larger, which is that, again, that top bound, it looks like our numbers are getting closer and closer and closer to 1 now instead. So basically, if you were to graph this, what would be happening is that on our first one, our values would just be getting larger and larger and larger. They would be increasing. For this one, our values would be leveling off at 1. And so we would have some sort of horizontal asymptote going along. But if you have any questions, please let me know. Like I said, as long as we're in school for tomorrow, we will be having our quiz. And then Friday, we will be continuing on to the next section of our series.